All right, so yesterday we talked about the three first rules in properties of logarithms. And now we're going to look at the last two with the change of base and the equality rule. So the change of base says I can change the base for any logarithm. So I have some logarithm with the base a, and I'm taking the log of x. I can rewrite it with a base of my choosing. You want to choose a base that you can actually take the logarithm of with your calculator. So we typically want to use log, which has base 10. So we talked about that yesterday. It's the common log on your calculators. So if you have the Pro, which I don't have the Pro at home, you can actually type in any base that you want. But without the Pro, with just the regular TI-30, and I'll show you with your cell phone too, you have a log button. This logarithm only has base 10. You do not have the option to choose any base that you want. But I can take whatever logarithm that I want. So this is saying 10 to what power gives me 5. Let's make that 50. So 10 to what power gives me 50? Well, it's going to be 1.698970004. So I can check it. 10 to that exponent. 4. This should be 50. And it rounds to 50 because this is a rounded number. So it's going to give me a rounded number. So we're going to use the change of base formula so that I can use a base 10 for any value that I have. So for example, if I have, and I'll do one that we can do by hand and then check it with the change of base. So if I have log base 2 of 128. So this is asking me 2 to the what power is equal to 128. So I can use my calculator with a change of base because maybe I don't know what this is. Maybe it's not nice. I can figure it out. So with my change of base formula, it is a logarithm divided by a logarithm. And I'm going to use base 10 because that's what I can use with my calculator. Looking at my change of base formula, the old base number, which is the a, is what I take the log of on the bottom. So here I have a log with base 2. So I'm going to take log base 10 of 2. So the old base goes in the bottom and it's no longer a base. And then the regular 128 is a 128 here. So you want to enter this in as a fraction. Is the easiest way to do it. So I have log of 128. I need to close the parentheses because I'm just taking the log of 128 divided by the log of 2. And it will tell me that my answer is 7. So this is telling me that 2 to the 7th power is 128, and it does work out that this is 7. So the change of base formula makes it so that I can take any base, right? It has two separate logarithms with a base of 10. So let me show you. I have an Android, but on my Android, I've got a calculator, right? If I turn here for me, if I push this button, it might work if you just turn your phone sideways, but you have more options in dealing with your value, and you should have somewhere on there a logarithm button. I know it's hard to read. I don't know why, but I do have a log button. So I'm going to put this in as a numerator and a denominator. So I had log of 128. I'm going to have to close that parenthesis and then divided by log of 2 and close that parenthesis. So using my cell phone, it's going to give me 7. All right, so you can do these logarithms on your own. If you have Desmos, I haven't researched to see if Desmos will change the base for you, but the graphing calculators have the regular log. The non-graphing calculators have a regular log with base 10, and your cell phones have a log with base 10. So you can take the logarithms while you're at home. Okay, so change of base is super important when I want to find some logarithm value that maybe I didn't know what it was. So I asked you to do some solving yesterday, and they all came out nicely. They may not come out nicely from here on out because I can use my change of base formula. All right, and then the other rule that we're going to talk about is the equality rule, which if you think too much about it. It makes a lot of sense. But if I have some logarithm with the base a and it equals x, and I have a different logarithm with base a and it equals y, if you're taking the log of the same base, these have to be equal to each other. So if I put some numbers in, let's say I take the log base 5 of 25. And this equals log is got to have the same base of 5 to some number y. So this is saying 5 to some number is 25. That number is 2. So I end up with a 2 here. So this needs to be the number 2. So 5 to that exponent of 2 needs to equal that number y. Well, that number y, 5 squared, is going to be 25. So this 25 has to be the same as this y. So, long story short, if you have a logarithm on both sides of the equation where they have the same base, one log on the left, one log on the right, you can cancel out the logs and just be left with the values. This only works if there's one log on the left and one log on the right. All right, so we're going to solve some logarithmic equations today. They're actually really easy to solve. I love logarithms. They are the coolest thing ever, and I really wish we could do these in person because I just love logs, but we can't. But solving logarithmic equations, they look super hard, but they're actually really easy. So there are two types. We're going to look at the two types. One type is where you have a log on the left and a log on the right. Now you're going to have a base. You're going to have a value. Right? And then we're going to cancel them out, the two logs out. So if we have a log on the left, log on the right, we get rid of them, and then that x equals y using the equality rule. My second type is where I have one logarithm on either the left or the right, and then I have a specific value, like a number over here. So we'll look at some of those. All right, so I've got 3 examples of type 1 with a log on the left and a log on the right. So for my first example, I have log base 3 of x equals log base 3 of 5. One log on the left, one log on the right. They have the same base. I cancel them out, and I have x equals 5. I'm now done. For my second problem, I have log base 5 of x plus 7 equals log base 5 of 2x minus 4. It's a little bit of algebra in here, but I have one log on the left. I have one log on the right. They have the same base. I don't need them. So I'm left with x plus 7 equals 2x minus 4. Oh, I can solve this just like a regular algebraic equation. I'm going to subtract x from both sides. So 7 is equal to x minus 4. Then I'll add 4 to both sides. So my x value is 11. I like to double check these just to make sure. So this would be log base 5. If I plug in 11, then I'll have 18. On the right-hand side, I'll have log base 5. If I plug in 11, I'll have 22 minus 4, which is 18, and it works out. You should get pretty decent answers for these. Not saying you won't have a decimal, but they should be relatively nice. For my third problem here, I have 2 logs on the left and 1 log on the right. I can't cross out 2 on the left and only 1 on the right. So I'm going to condense and make this one logarithm on the left. So if you have multiple logarithms on the same side of the equation, condense them like we did yesterday so that you have one log. My base here is 10. It's invisible, but there is a base 10. But if I put these together, there's subtraction. So I have log, and then I have x divided by 10. And then the right-hand side didn't change. I have log of 5. So you're going to have to condense if you have 2 logs on one side of your equation. They both have 1 log on each side with a base 10. They are gone. So x divided by 10 is equal to 5. I'm going to multiply both sides by my denominator, which is 10. So my x value is 50. And I can check it back in here. 50 divided by 10 will give you that 5. All right, so if you have logs on both sides of the equations, you're going to put them together, condense if you can, and then cancel out the logs. All right, so for my second type of problem, there's only logarithms on one side of the equation. So if I look at number 4, I have log base 5 of 32 equals x. If I were to rewrite this as an exponential, I would have 5 to the x power equals 32. And I should notice that this will not be a whole number because 5 squared is 25 and 5 to the third is 125. So it's going to be between 2 and 3, definitely closer to the 2. So, wait for it to focus. Why does this? Okay. So, if you cannot solve it as an exponential, then maybe I can solve it as a log. So I can take this log and use my change of base formula to find the value of x. So when I use my change of base formula, I'm going to use base 10 because that's what I can use in my calculator. The old base number goes in the bottom. It is no longer a base. And then I have my 32 on top. And this is going to equal the same x value. All I did was rearrange my logarithm as the quotient of 2 logs. All right. Now I put this in as a fraction. I have log of 32 divided by log of 5. And I get 2.15338279. I'm going to round it to 2 decimal places just to give me a good estimate. So x is 2.15. I'm going to check this and make sure that it works by raising 5 to that exponent. So 5 to the 2.15, I rounded. So it's going to be rounded, but it should be pretty close to 32. Pretty close to 32. All right, for my next one, number 5, I cannot use my change of base formula because I don't know what this specific value x is. So when you have one logarithm, rewrite it as an exponential. So if I rewrite this, it will be 7 to the 100th power is equal to x. Oh. I can multiply 7 by itself 100 times. Okay, I won't, but the calculator will. So 7 to the 100th power, it is a rather large number, as evidenced. Now we'll get it to focus. So the calculator writes it in scientific notation, because if I multiply 7 by itself 100 times, I'm going to get a really large number. So here's my scientific notation. You might see an E there. It represents the same thing. So my answer here is 3.23. So I'm still going to use 2 decimal places or 2 significant figures times 10 to the 84th power. Big number. All right, and then for number 6, I have 2 logs on the left and then no log on the right. So again, anytime you have 2 logs on the same side, you're going to condense them together to make them into 1 log. So it's an addition problem, so I'm going to do this as multiplication when I combine. So I have log base 3 of x times 5, and that equals 12. So I condensed, the right side stayed the same. I cannot use my change of base formula because I don't know what x is, but I can rewrite this as an exponential. So 3 to the 12 equals x times 5. So I just need to figure out what is 3 times itself 12 times. That's going to be a big number too. So 3 to the 12th. 5, 3, 1, 4, 4, 1. And this equals x times 5, or 5x. If I divide both sides by 5, I get my answer. So divide by 5. I get 106,288.2. These typically are going to give you grosser decimals and just round them to 2 decimal places for your final answer. All right, so 2 types of logarithmic problems, and then I have some practice for you. I will be specific into which numbers I want you to solve. Let me know if you have questions.